Hi everyone. Today's lecture is going to deal with the way in which we can represent graphs to use with the computer. Okay, so we are going to study different data structures that we can use to store the information of a graph and then use this information for our computations with the computer. Okay, so the first thing that we need to define is what we call adjacency. Okay, so imagine that we have a graph, either directed or not, and we have an edge in this graph. Okay, this edge is UB. It goes from U to B if it is a directed graph, and it goes from U to B and from V to U if it is not directed. Okay. Um, if the graph is directed, we say that V is adjacent to U. Okay, so if we can go from if we can go from U to B, then we say that V is adjacent to U. Okay, so adjacent vertices are those that we can reach from a given vertex. Okay, in the case of a graph that is not directed, then this adjacency relationship is symmetric. Okay, because if I can go from U to B, I can also go from U to B. So from B to U. So in that case, we had like a double arrow. We can go from U to B and also from B to U. So both vertices are adjacent. But in the case of um, directed graphs, this is not the case. For instance, in this example here, we have these two vertices and this edge from 6 to 3, and then 3 is adjacent to 6, but 6 is not adjacent to 3. Okay, so adjacency is a relationship between vertices, and those vertices that are adjacent to a given one are the vertices that we can reach with an edge. Okay, so for instance here, in addition to 3 being adjacent to 6, 1 is adjacent to 4, but 4 is not adjacent to 1, and 5 and 4 are both adjacent to each other. Okay? In the case of the undirected graph, 1 and 2 are adjacent, 2 and 5 are adjacent, 1 and 5 are adjacent, and 3 and 6 are adjacent. Okay, so in this case the relationship is symmetric, as we have already said. Okay, so what is this adjacency concept good for in order to represent the information of the graph in a computer? Well, the idea is that we can store this information in a matrix. Okay, what we call the adjacency matrix of the graph. Let's start with a graph that is not direct, that is directed, a D graph. Well, how can I reach? Well, let's start with a graph that is directed with vertices from A to N. Okay, so we have N vertices. What we are going to do is to represent the information of the graph in a matrix which has N rows and N columns. Okay, so it's N times N, the dimensions of the matrix. Okay, and in the position ij, we are going to start to store a 1 if j is adjacent to I. So if there is an edge from I to j, we are going to write a 1 in the position ij of the matrix. Okay, so in row I, column j, we write a 1. And if there is no such an edge, then we write 0. Okay? And we can see that this matrix represents the adjacency relation. If we have this matrix, we can know which vertices are adjacent to which vertices. And in fact, we have all the information about the graph because we can deduce what are the edges on the graph, and the number of vertices is given by the number of rows and the number of columns. So with this matrix, we have all the information about the graph. Okay? And this is what we can use to store a way in which we can store the information of the graph in order to use it with the computer. Okay? Take into account that since we are dealing first with directed graphs, this adjacency matrix is not in general symmetric, because we can have an edge from, let's say, 2 to 4 without an edge from 4 to 2. So element M24 will be 1, but element M42 will be 0. Okay, so in general, it is not symmetric. If we are using a not directed graph, then this matrix will be symmetric. Okay, and in general, we can use this representation for any kind of graph. We can also use it for non-simple graphs, for multiple graphs, but in that case, multiple edges are not properly represented by the matrix, because we only use a 1 or a 0. If we want to use this kind of representation for a graph that is multiple, that has multiple edges between pairs of vertices, then we can extend the notation, and instead of using zeros and ones, we can use any natural number. So for instance, if we have 3 edges between from vertex 2 to vertex 5, then in the position in the row 2 column 5 we write a 3. We write the number of edges that connect those vertices. Okay, but since we are not going to work with multiple edges very many times, we are not going to need that kind of representation. What is important to notice is that loops, that is edges that start and end in the same vertex, are well represented in the matrix, okay, because these loops are going to be present in the main diagonal of the matrix, okay, because the number of the row and the number of the column is the same, because they start and end exactly in the same vertex. Okay, cool. So let's give an example of what is the adjacency matrix of a graph, in this case a directed graph. Okay, so we have here a graph with 6 vertices, so then we have a square matrix with 6 columns and 6 rows, okay, 6 by 6. And we are going to write a 1 for each of the vertices or the edges that we find in the matrix. Okay, so let's write here all the edges in the matrix, and we find that we have edge 1, 2, we have edge 2, 2, we have edge 2, 4, we have edge 2, 5, we also have edge 4, 1, we have edge 4, 5, edge 5, 4, and we have edge 6, 3. Okay, in total we have 8 edges, 1, 2, 3, 4, 5, 6, 7, 8 edges, and that is going to be the number of ones that we find in the matrix. Okay, so we have exactly 1, 2, 3, 4, 5, 6, 7, 8 edges in the graph, 8 ones in the matrix. Okay, in this case, notice that this one here comes from edge 1, 2. We are in row 1, column 2. This is an element that corresponds to the edge that goes from vertex 1 to vertex 2. Okay? In the second row, we have this 1 that is in position 2, 2. This corresponds to the loop 2, 2. Remember that all the loops are going to appear in the main diagonal of the matrix. Okay, in this case we only have one loop, so there is only one loop in the diagonal. Okay, we also have this one here which corresponds to edge 2, 4, this one here that corresponds to edge 2, 5, and notice that in row 3 we have no 1 at all, because there is no edge coming from vertex 3. Okay, there is an edge arriving at vertex 3, and that will appear in column 3, but since there are no edges coming from vertex 3, we have no ones on row 3. Okay, the next row corresponds to the edges that come from 4, or to put it in another way, these are the vertices that are adjacent to 4. Okay, so we have edge 4, 1, 1 is adjacent to 4, so we have 1 in position 4, 1. Also, we have edge 4, 5. 5 is adjacent to 4, so we have 1 in position 4, 5. Also, we have this edge here from 5 to 4, so here we have a 1 in position 5, 4, because 4 is adjacent to 5. And finally, we have this edge 6, 3, and then a position 1 in position 6, 3. This is to state that 3 is adjacent to 6. Okay. Also notice that this matrix is not symmetric. For instance, we have let me use a different color. We have this one here, but we have a 0 in position, in the symmetric position. We have a 1 in position 1, 2, but we have a 0 in position 2, 1. Okay, so this matrix is not symmetric, okay, because this is a directed graph, and in this case we do not have edges going from a vertex to the other and the other way around in all the cases. Okay, it is true that we have, for instance, an edge going from 4 to 5 and an edge going to 5 from 5 to 4, and that reflects in the matrix because we have these two positions that are symmetric and they are both 1 at the same time. But this is only because in this case we have edges connecting 4 and 5 and 5 and 4. Okay, so in general, whenever we have a connection that is from 1 to whatever, from U to V, but we have not the connection from V to U, the matrix is not going to be symmetric. Okay, so let's see now the adjacency matrix of a non-directed graph. Okay, so now we are going to use this example in which we have six vertices again. So we are going to use a matrix which is 6 by 6. Again, a matrix 6 by 6. But now we have an undirected graph. The graph is not directed, okay? And this is going to change a little bit the way we represent the information in the graph, okay? Because now each edge is going to connect both vertices, okay? So if one is connected to 2, that means that both are adjacent to each other, okay? So please now stop the video, try to compute the matrix for the adjacency matrix for this graph. Check that it is symmetric. It must be symmetric because it is a non-directed graph. Okay, so pause the video and try to compute the matrix and come back to the video. I'm going to give you the matrix in the next slide, but I want you to try to do it on your own. Okay? Okay, have you been able to do it? Are you back here? Let me then give you the answer to this question. Okay, so this is the matrix that you should have gotten from this graph. Let's check that this is correct. Okay, so let's do exactly what we did in the previous case. Let's grab the different edges and see where they appear in the matrix. Okay, so here we have edge 1, 2, but remember that since this is a non-directed graph, this is equivalent to having edge 2, 1. Okay, we also have 1, 5, which is equivalent to 5, 1 because the graph is not directed. We also have 2, 5, which is equivalent to 5, 2. And we also have 3, 6, which is equivalent to 6, 3. Okay? So we have 4 edges, but now notice that in the graph we have not 4 ones, we have 8 ones. Okay? We have 1, 2, 3, 4, 5, 6, 7, 8, because each edge now appears twice. Okay, appears twice because edge 1, 2, for instance, also appears as edge 2, 1. Okay, so this is a bit different to what we had before. Now we have each vertex, each edge represented twice in the matrix. Okay, so let's see where all these edges are appearing and check that in fact this is the matrix that represents this graph. Okay, so 1, 2 appears here in position 1, 2 and also appears as 2, 1. 1, 5 appears here in position 1, 5, but also appears here in the symmetric position, in position 5, 1. Okay? Notice that 2, 5 appears here in position 2, 5 and also in position 5, 2. And finally 3, 6 appears here, row 3, column 6, and also here in position 6, 3. So in fact this matrix is symmetric as we expected because the graph is non-directed and each edge appears twice in the matrix. Okay? Before we follow on, I want you to notice that these matrices are useful to represent the information about the graph. We have all the information, we have the number of vertices and which have all the edges. In the case of a directed graph, each one is an edge, and in the case of a non-directed graph, each edge appears twice in the matrix, okay? So we have all the information. We have the edges, we have the vertices. But we also have another piece of information that we can quickly recover from the adjacency matrix, which is what we studied in the previous lecture, which is the degree of a vertex in the graph. I think this is better understood first with the case in which the graph is not directed, and we come back to the directed case. So remember that the degree of a vertex in a directed graph is the number of edges that are incident in that vertex. So for instance here, vertex 1 has degree 2, vertex 2 has degree 2, vertex 5 has degree 2, and vertices 3 and 6 have degree 1, and vertex 4 has degree 0. Okay, so how can we get that information from the matrix? We can get that information very quickly, because if we compute the sum of the rows or the sum of the columns, it should be the same because the matrix is symmetric, we obtain exactly the number of edges that are incident in each graph. Because for instance in row 1 we have the number of edges that come out of 1. Okay, so here if we compute the sum of the first row, we obtain 2, which is the degree of 1. In the second row we obtain as the sum again 2, which is the degree of 2. In row 3 we obtain as the sum 1, which is the degree of 3. In row 4 we obtain 0, and that is the degree of 4. In row 5 we obtain 2, and in row 6 we obtain 1. So this is the total number of edges that are incident in each of the vertices, that is the degree. If we do the same with the columns, we obtain exactly the same: 2, 2, 1, 0, 2, and 1. Okay, because the matrix is symmetric, so the columns and the rows are exactly the same. Okay, if we go back to the case of the directed graph, then remember that we have two notions. We have the in degree and the out degree. The in degree is the number of edges that arrive at a given vertex, while the out degree is the number of edges that come out of a given vertex. Okay, so in this case, for instance, I'm going to write first the in degree. We have that for 1, the in degree is 1, and the out degree is also 1. In this case, for 2, we have that the in degree is 2, and the out degree is 3, because there are 3 edges coming out of the vertex: the loop and the edges that go to 4 and 5. 3 has in degree 1, out degree 0. 4 has out degree 2 and out degree, and in degree 2 and out degree also 2. And 5 has in degree 2 and out degree 1. And 6 has in degree 0, out degree 1. Okay, and remember that the total degree of a vertex is the sum of the in degree plus the out degree. Okay, so in the case of 1 this is 2, in the case of 2 this is 5, and so on. Okay, so how can we get this information from the matrix, from the adjacency matrix? Again, we need to compute the sum of columns and matrices, but in general now we are not going to obtain exactly the same number, because the matrix is not symmetric. Okay, so in general, we are going to obtain different numbers. Okay, so how do we know what number is the degree or the in degree or the out degree? Well, remember that in a row we have represented the vertices that are adjacent to the vertex in that row. Okay, so that is the number of edges that come out of that vertex, because adjacent vertices are those that we can reach from the given vertex. Okay, so in order to reach another vertex with an edge, we need the edge to come out of that vertex. So if we sum the rows, we should obtain the out degree of the vertex. Okay, and here notice that the out degree of 1 is exactly the sum of the elements in row 1. Okay, it's 1. In the case of 2, the out degree is, yes, it is indeed 3. In the case of 3, the out degree is 0. In the case of 4, it is 2. In the case of 5, it is 1. And in the case of 6, it is 1. Okay, so this sum of the rows gives us the out degree of each of the vertices. Okay, and if we sum the columns, we obtain the vertices that arrive, the edges that arrive at a vertex. Okay, so that is the in degree. So in the case of this matrix, if we compute the sum of this column, we obtain 1, and that is the in degree of 1. In the case of the second column, we obtain 2, that is the in degree of 2. In the case of 3, we obtain 1, that is the in degree of 1. In the case of 4, we obtain 2, the in degree of 4. For 5, we obtain 2, it's in degree, and for 6, we obtain 0, and that is exactly the in degree of 6. So again, we have the in degree and the out degree. We have the degrees as a information that we can quickly obtain from the representations in adjacency matrix. Okay. Notice also that if we want to compute the total degree of a vertex, we need to compute the sum of the elements in the row and the sum of the elements in the column. Okay, and notice also that then the elements in the diagonal are going to be counted twice. Okay, for instance, for 2, we have that the in degree is 2, that is the sum of the elements in the column, and the out degree is 3, that is the sum of the elements in the second row. And that is exactly the total degree of the vertex, it's 5. Because remember that loops are counted twice. In fact, we have to take a loop at 2 and see how many extremes of the edges are touching the vertex. So we have 1, 2, 3, 4, 5. Loops are counted twice. And since loops are represented in the main diagonal of the graph, when we compute the sum of the row plus the sum of the column, the loops are going to, the elements in the diagonal are going to be counted twice, and that is exactly what we need and what we expect. Okay, so we have this representation in which we have all the information about the graph. We have the number of vertices, we have the edges, both in the case of directed graphs and undirected graphs. And we also have a way to compute information about the degrees very quickly. Okay, so this is a convenient representation in some situations because we have all the information that we need and we can compute some properties. We will see that later on we can compute other important properties of the graph from this matrix, okay? But this representation also has some drawbacks, has some inconvenience. The main inconvenience of this representation is that in general, the number of edges of a graph is not the total number of positions in the matrix. Okay, in general, we have not as many edges as we can represent in the matrix. What I'm trying to say is that in a graph there is in general no connection between all the possible pairs of vertices. Okay, so in practical situations we many times deal with what we call sparse graphs, where the number of edges is much much less than the square of the number of vertices. And notice that in the matrix we are representing the number of vertices squared, because we have n rows, we have n columns, so we have n square positions. So that is a lot of memory. Okay, imagine that, for instance, we have a graph that represents the users in a social network. So maybe in Facebook, I don't know, there are like 3 billion users. Okay, 3 to the power 3 times 10 to the power 9. Okay, so the square of that, if we have about, let's say, to make it simpler, we have the number of vertices equal to 1 to the power 9. Then the number of connections, of potential connections, is 10 to the power 18. That is a very big number, okay? If we need to represent that number of possible connections as a matrix in the computer, that is going to use a lot of memory, okay? And we are going to be wasting a lot of this memory, because most of that positions are going to be 0. I don't know what is the average number of friends of somebody in Facebook, but let's say that is, I don't know, 1,000. Okay, 1,000 is a lot. That is a lot of friends. Let's say maybe 10,000. Okay. But even if it is 10,000, then the number of real connections is 10 to the power 4 times 10 to the power 9. The number of users times the number of real connections that they have. And I think I'm really being generous with the number of friends. Probably the average number is less than that. Okay. But let's say that it is of this order, and we have then 10 to the power 13. Okay, so when we compare these two numbers, 10 to the power 18 is much bigger, is 10,000 times bigger. So we are wasting a lot of memory. Most of the elements, only 1 out of 10,000 is going to be different from 0. Okay, so this is something that for sparse graphs, for graphs in which most of the elements are 0, and in most practical situations this is going to be the case, is a waste of memory. Okay, and then we need to look for a different way of representing this information. Okay, because it's not practical to use this in a computer, to represent matrices of this size, to have them mostly empty. Okay, so what we are going to do then is to use a different representation, what we call adjacency lists. Instead of using adjacency matrices, we are going to use this representation in which for each of the vertices in the graph, we store a list, that is why we call these adjacency lists, this representation adjacency lists, in which in each of these lists we store the vertices that are adjacent to a given one. Okay, so we only store the real vertices that are connected to the one that we are studying. We don't store all those zeros. Okay, for small cases, and what we are going to do here with small examples, adjacency matrices are very convenient, but in practical applications, as you can see, they can be a waste of memory. So we are going to store only those elements, those edges that are really present in the graph. Okay, and in this case, then instead of having to use a memory that is proportional to the square of the number of vertices as we had in the previous case, we are going to use a memory that is proportional to the number of edges in the graph. Okay, and that is in general much less than the number of vertices squared. Okay, of course, for dense graphs, for graphs in which the number of edges and the number of vertices squared is more or less the same or are comparable, then we can use adjacency matrices. Okay, but in general, that is not the situation that we are going to find. Okay, so how do we define and use these matrices? Let me give you an example first for directed graph, and then for a non-directed graph. Okay, so let's go back to our example with 6 vertices, and remember that now what we are going to store is a vector that has in each position a list with the vertices that are adjacent to a given one. Okay, so the size of the vector is the number of vertices, and so because it has a list for each vertex in the graph, and the list in position I contains the vertices that are adjacent to I. Okay, so in this example we have 6 vertices, so we are going to have 6 lists, these 6 lists here, so this is going to be a vector of lists, and in position 1 we are going to store the vertices that are adjacent to 1. Okay, for instance, in this case the only vertex that is adjacent to 1 is 2. In position 2 we are going to store all the vertices that are adjacent to 2. In this case 2, because there is a loop, okay, 4 and 5. Okay, in position 3 we are going to store the list of the elements that are adjacent to 3, but there is no vertex that is adjacent to 3, so this list is empty. This can happen, of course. Okay, this is similar to what happens with the adjacency matrix when we have a row that is completely zeros. In position 4 we are going to store the elements that are adjacent to 4, which are 1 and 5. In position 5 the vertices that are adjacent to 4, which are to 5, which is only 4, and in position 6 the vertices that are adjacent to 6, which is only 3. Okay, so